detection of symmetry angles. So given the initial task specification, we need to calculate, for convex polygon we need to calculate the lines of symmetry, which obviously rely on the existing points. For that we need first consider the following. So we got the polygon of with vertices starting 0, 0, starting 0, 0, then 1, 0, 1, 1, and 0, 1. For every polygon we should first perform the following. We know that every line of symmetry goes through the center of mass for polygon. Given that, and potentially it also as potential candidate for the line of symmetry could go through the midpoint. So first we could calculate the midpoints. So add the midpoints for this for the polygon. So in other words, that is described in the proper test, where we perform midpoint calculation. So we add additional points which lie in the middle of the appropriate edges. Then afterwards we perform the translation to the center of mass. So the basic polygon point would be translated accordingly, and then once translated, we could evaluate the potential candidates, which is represented here as get angles of symmetry. Angles of symmetry. Angles of symmetry. Symmetry angles. Check symmetry and get symmetry angles. These symmetry angles essentially calculates all the potential candidates. Here specifically, those are identified by points in the first half, so above 0x, above or x-axis. Here specifically that this point, this, and this. So this way, these are only candidates, angles candidates. Specifically in this specific case, this angle starts with 0, and according to the test, get angles, symmetry angles, symmetry, lines, angles, get symmetry angles. So potentially, yeah, start with 0, then p divided by 4, p divided by 2, and 0, p divided by 4, p divided by 2, and 3p divided by 4. After that, we need to figure out how to check the symmetry itself. And for this we need so-called representation um, of D and some kind D and alpha representation. What is it? Specifically, it calculates for every edge, left to right, starting from the beginning point. It calculates an angle and its length. For example, here it would be 1, then it goes angle between o x-axis, which is in this specific case 0. Then pretty much the same for the second edge, but here edges narrowed down, and also takes lines of symmetry into consideration. That is why we got the following. We got the first point, the first edge 1 and 0, the second one also comes as 0 half and 0 and 0 half and 0. So it is divided by 2, since we need only take the halves of the original edge. Then after this representation is calculated, we are able to perform the following. We could take the following approach. So we would like to calculate how many of these sub-edges edges are placed above and below their original below after translation below and above the OX axis. So for in the case we are taking those edges which are above, it would be one point and half. Then angle with OX is p divided by 2. Then for the second sub edge we got half. Angle with OX is p. Then once again 0 and a half. The angle with OX is once again p. Afterwards it is minus p2 or 3p 3p2. It will be 3p2, and that is it. We don't and this point already belongs to the lower half according to the way we organize this approach. And below those points would be once again 3p 0 and a half 3p2, then 0 0 and a half that is the length, 0 and a half, then it is 2p, or in other words that is 0 could be considered as 0 or represented as 0. Then once again 0 and a half, then 0, and then we got the same angle as in the first point. So it's 0 and a half and p2. Then we need somehow to compare the pairs above and below, and for this we need perform the reverse check. So this we need to compare with this, and this with this. otherwise round. Hold on a second. The first we compare with the last. So, but it is not a direct comparison in this specific case. We need to minus symmetry check symmetry, and we need to make it consider equal, but we need from P substitute the P on 2 for those which are above. In other words, that identifies the symmetry. And for this specific use case, we could see that once we, for lower half, substitute the angle from P, those would be 100% equivalent. Obviously, it works in pretty much the same way for any cases. So the very representation of an angle goes down to the articles which are already written in 1970s approximately. But as we could see after performing the debugging, so after running all the tests, everything runs smoothly. So all these substages could be observed once we evaluating the appropriate tests. From interesting aspects which could be considered, the ability to, the necessity to for example, for triangle, perform the check with respect to epsilon, which is a usual approach for comparison of doubles. So that is the only scenario where it was directly required. And you could take a look at this matcher, so which performs pretty much the same stuff as we require. And that is it, that's simple. So this way we, after all these checks, all this procedure, we are able to calculate on the lines on symmetry. Then we need to perform indexing, reverse indexing in the original representation itself. And after reverse indexing, we could, given the property of symmetry, we could actually simply plus this point, so circle it around like in for example in mathematical group, and get the next point we need, and to get the pairs from it.